Before I get into introducing Larry and today's subject, a couple of things I want to say. So there was a registration card that you all filled out, and I want to remind you that there's a raffle for some pretty neat prizes at the end of the lecture, so hang around for that if you don't have to run off to violin or soccer or fall ball. I want to say that one of the reasons that we do this is for you to learn about Yale's science at Yale, and to learn about the opportunities there are for students in the community to come to Yale. And many of you have the mistaken impression that it's really expensive to go to Yale. Just this last year, our financial aid office has changed their policies such that if you're a single parent and your income is under $75,000, if your child gets into Yale, it's free. Now that's not just free tuition. That's room and board. It's cheaper to send them to Yale than to keep them at home. And that's true for families with incomes upwards of $200,000 a year. You'll be guaranteed that only 10% of the family income above that $75,000 will have to go towards that total term bill. So even for them, it's cheaper than keeping a teenager at home. I had 6, I know. Much cheaper. So it's a real pleasure today to have Professor Larry Gladney. Larry is going to tell you a little bit about his background, but he's born in Mississippi, went to school in East St. Louis, got a degree at Northwestern, went to Stanford, and then ended up at Penn as a postdoc, and then just rose up through the ranks. Became a full professor and eventually the dean of science at Penn, and we were lucky enough to steal him away a couple of years ago and bring him here. And so it's with great pleasure for me to introduce Professor Larry Gladney.
Good morning, everybody. Can you hear me? Can you hear me okay?
Yeah.
All right. Well, first of all, thanks to Professor Zilm for inviting me here. Thanks to all of you for coming out to celebrate science on Saturday. Not to scandalize anybody, but if I take off my shirt, I have a March for Science t-shirt on underneath this, which is basically an expression of the fact that in our society, science has become so important and yet so marginalized in terms of how much time and effort we spend thinking about what it's added to our lives. So what I want to do today is to actually give you about 50 minutes, 45 minutes of talking after all the great demonstrations outside, which I well remember doing many Saturdays at Penn. And in that talk, what I hope that you take away from this is that there is so much more yet to be done, yet to be discovered, that if you are at any age, no matter what it is, from 15 to 95, there is still really exciting science which is coming in the next 10 years, which you can actually be a part of. This is through what's called citizen science, but whether you're a person who's just simply interested in following along over the internet at home or getting involved in the many projects that take place at Yale, science is something that can be a part of your life and probably should if you're excited at all by any of the ideas I'm going to talk about today. So to begin with, I'm supposed to say a little bit about my background, and I'm going to spend basically just 1 minute on that, which is to say that the path to becoming a physicist varies tremendously. So my story is not at all typical, as you might expect, but it's also the case that it's not typical for pretty much anybody who's ever been a graduate student or postdoctoral scholar with me. We all came to physics in very different ways. I happen to be the kind of person for whom physics has always been it, right? It was like a religious epiphany for me to discover it at age 12. And I had always been interested in it since before I can remember. And that's because from the age of 3 or so, my uncle tells me, I've said I wanted to be a scientist, but a scientist who was interested in just 2 really important questions for me. And that is, what are the big questions that we can ask about how the world works. And if you get into thinking about it just for a little bit, what you realize is that those two big questions that have been around for at least 2,500 years in our societies are, what is the world made of and what holds it together? All right? And so from a very early age, I've been motivated by trying to understand what's the answer to these questions. Now, the fact that it's something that you can be thinking about at age 3, 4, 5 is not really so relevant as the fact that we've had more than 20 centuries of people trying to understand how to answer those questions. And what we've come down to is, first of all, we've identified the set of people who are strange enough to be spending most of their life thinking about that, which is the set of people who are called physicists, and the science is called physics. That's not that other people in other disciplines don't think about this. It's been thought about from the point of view of philosophy. It's been thought about from the point of view of other branches of science. But it's the physicists who actually have this on their T-shirts and if they're a union card, if you want, that says that these are the questions that we are particularly responsible for trying to figure out if we can get to an answer that we believe. The answer has to, however, be in a form which scientists will respect is something that we, first of all, are able to reproducibly study, and that we're also able to explain in 3 different ways. All right? So one way is through math and equations. Another way is through experiments, that is, observations. And then the third way is to do what I'm doing to you today, which is to try and explain it in common sense language. And to do that, we have to rephrase the question from the ones I asked up there. They're the same questions, but we ask them in languages which allow us to explain them in those 3 different ways. So what are the fundamental constituents of matter? What are the fundamental forces? The reason we do that is that forces and constituents are things that can be observed in the laboratory. We can see what their actions are, we can study them, and by virtue of reporting what those observations are in common sense language and in terms of equations, we can actually do the mission or complete the mission. The problem is that these are so hard that it's taken us really, as I said, more than 20 centuries to even come up with an approximation of what we think is a believable answer. So if we go back to the beginning, this was something that has been thought about, I said, probably more than 2,500 years, but at least around 550 BC, on a little island port city called Miletus, we do have historical records that show that there were 5 people who were really thinking very intently about those 2 questions. And so, just because it's historical, I like to say what their names are, right? So it's Thales of Miletus, Anaximander, Anaximenes, whose portrait is actually shown up there on the left, Democritus, and his teacher, Leucippus, those 5 people. Now, the first 3 of those were really concerned with the idea of how do you ask the question so that you can answer it in the 3 ways that I just talked about, right? So they are the first people to say that you have to be able to both predict it with math, you have to be able to show it in observations, and you have to be able to explain it in plain language. So those 3 are the people who first said that's the standard by which we understand that the questions either can be answered or are answered by anything that we've done in terms of our studies. The other 2, Democritus and Leucippus, I'll come to in just a minute. All right, but Anaximenes is the person who you probably remember most for what he sort of said the basic elements are, right? Earth, water, air, and fire. Now, in fact, if you go into the history, what he actually said was that everything is made of air. So he was the first person that we know, there might have been others, but he's the first person that we know actually decided that air was something that could feel different in observations and, like water, could actually be different in terms of how you touch it and interact with it depending on what state it was in. And what I mean by that is water, for example, can be a liquid, but if you make it very cold, it becomes a solid. If you make it very hot, it becomes a gas or steam. And so he was the first person to realize, and the observation that that was something that could actually be true for most things in the universe, started with him with a very simple observation. It's kind of unbelievable, which is he blows on his hand and he realizes that if his mouth is open, it feels warm. And if your mouth is closed, it feels cool. But it's the same stuff, right? So how does it have these two different properties? So he was the first one to write down that, in fact, the way in which we affected the density of things actually determines how they appear to us in experiments. So he actually said that the stuff we call air makes up everything. That's the fundamental constituent. And earth and water and fire are just various versions of how air appears depending on the particular properties that it appears to have on the basis of its density. Now that's a wrong idea, right? But it got people started. And so Democritus and Leucippus, who I just mentioned before, in just a few years after this theory had taken hold, said, okay, it's not air, right? Everything is not made of air. We don't actually know what it is, but they abstracted the idea to something that was very powerful for us. So what they did was to say, if you take anything, no matter what it is, and you cut it in half, and you take one of those halves, and you cut that in half, and you take that, and you cut that in half, and you keep going on and on and on, they're the first ones to actually argue that eventually you get to something that can't be cut. That in Greek is called the atomos, which we abstract to the atom. And so they're the first people that we know to write down a theory and influence others to say that eventually everything has to be made of something that is irreducible. It's as small as you can get, and everything else is built by putting those pieces together in various ways, again, following Anaximenes' observation that putting it together in various ways could give it different densities, and different densities could make it appear as though it was different, even though it's actually all the same stuff. So that idea is so powerful that we've kept it, as I said, for 2,500 years or so, and that's called the atomic theory. Now, believe it or not, the atomic theory, even though I said we've kept it for 2,500 years, it hasn't always been in vogue. That is, no one can see an atom, and consequently there were many people who believed that they were fictions, right? They're a nice idea, they're a way of thinking about how you go about breaking things down to get to the fundamental constituents. So that idea remained, but the idea that atoms themselves could actually have existence was not. So as recently as 1909, the chair of chemistry at the University of Chicago simply pronounced atoms as fictions, right? Convenient, but not really real. And so it's been only in the last century that we've actually had the ability to say, we understand science well enough that not only do we think that atoms are a good idea, we actually believe that, in fact, everything is made of atoms. But what has changed in terms of the original idea from Democritus is that these atoms can appear in different forms. In other words, not only in terms of their density and how they're put together, but there isn't sort of one kind of atom. There are actually, roughly speaking, in nature around 92 or so different kinds of atoms. And the way in which we determine that has happened is by going into this cutting experiment, dividing things in half and taking that and dividing it in half and taking that and dividing it in half. And so what we wind up doing is going through a chain in which we take the smallest things that we can see in a microscope, like a virus, and if we put that into a particular kind of experimental apparatus that allows us to divide it or to look at it in even more fine resolution with things like X-rays as opposed to visible light, then we eventually can see that it's made of molecules, and the molecules are made of the things that we call atoms. The atoms are, at the point of their discovery, around 1913, were the irreducible. That is, people could not figure out a way to get anything smaller than that. However, after a few decades, we were actually able to not only theorize, but then experimentally discover and explain with math that, in fact, the atom, what we call the atom, we had pulled the trigger too soon, right? That the atom, in fact, is not irreducible. It is made of still smaller stuff. The nucleus, as I said, was discovered around 1913. Then around 1918 or so, it was understood that the nucleus itself was made of something called protons and neutrons. And then the protons and neutrons we discovered around 1967, were made of still smaller things that we call quarks. But at that point, which is right now, from around 1968 or so to now, we think that quarks and the things that surround the nucleus, called the electrons, those are the smallest irreducible elements of matter. We have not yet seen anything that's smaller, and we probably won't, because even though we might come up with more powerful microscopes, more powerful ways of cutting things in half and try to focus that on the quarks themselves have been theorized, and we pretty much believe that the theory is correct, cannot ever be seen by themselves. That is, we've actually now gotten to the point where we think we're firmly convinced that something exists which can never itself be seen. It can only be seen in combinations with other things. And that means that we will never, if that theory is true, be able to take a single quark and divide it up. That is a problem only for philosophers, right? Physicists actually don't care because, again, we can explain it in terms of equations, we can explain it in terms of observations, and we can explain it in terms of simple language by just saying what I just said. That is, there's no way to take it, even in principle, and divide it up into something that's still smaller. Now, of course, anybody who makes that pronouncement is on very shaky ground. Physicists don't like making predictions that we will never do something or that something will always be true. Nonetheless, the best studies that we have right now indicate that that's true. The math part of this comes in the fact that we've been able to say the quarks themselves are, and electrons are what everything is built out of, but it's actually the atoms that is the functional part of Anaximenes' description of how things are constructed to make a whole universe, which is to say we have this periodic table of elements. Those are all the different kinds of atoms that there are. Now that in and of itself allows us to do a tremendous amount of technology, right? We can actually make all kinds of things work and understand the principles by how they work by understanding nothing more than what's in that table. So everything beyond that is only for the joy of the people who like looking at hard problems and saying, is there anything more to be discovered? Eventually, there may be practical concerns that come out of those kinds of studies, but those practical concerns are not what directly drive us. It's the way that we get there that does. Along with understanding what the fundamental constituents are, though, we have to understand what holds them together. And those are called the fundamental forces. Fundamental because all kinds of forces that you might think of, like friction, right? What makes it possible for me to walk across the floor, which would be much more difficult if there were no friction or very little friction like ice. All of those forces can be made of, or can be seen as being just different manifestations of one of the fundamental forces. The one that we're most familiar with is electricity. Another one that seems to mystify us, or at least mystify most people, is magnetism. But there are other forces that we've learned are fundamental that we can actually manipulate. For example, nuclear forces. And so nuclear reactors are simply manifestations of forces that only operate on the distance scale of nuclei or neutrons, but they can be turned into a practical way of generating electricity, and electricity is the thing that sort of drives our current society. Now there's one other force which I'm going to mention, which is called gravity, but I'm going to come back to that one. Gravity is the most mysterious of the forces, actually, even though it's the one that's probably most familiar to everyday people because it holds us down to the earth. It keeps things going down instead of letting them go up for any length of time. But it's in fact the most mysterious to understand, and the rationale for that's a little complicated, but it has to do with the fact that in order to understand the equations for these guys, ultimately, we have to depend on something called quantum mechanics or quantum physics, right? And we don't yet have a quantum physics theory for gravity. So even though we can explain a lot about how it operates, we can't come up with an equation that actually explains its operations in the same way that we can for the other three forces. So that's kind of a shame. It drives a lot of research that takes place today, including my research, but for reasons that I'll come back to a little later. Now, in and of itself, the picture has to be, again, once again, abstracted. And the reason is that physicists don't like memorizing lots of names of things. And consequently, the periodic table, we know that it exists, and that's probably good enough for us. We can identify most of the elements that we see on it in terms of what their chemical properties are. But really, we have to understand how to get equations to work. And it's too complicated to do it with the picture that we talked about before. So we abstract it by saying there's two forms of existence. There's matter, and there's energy, which holds the matter together or pushes it apart. And those two ideas are connected by the most famous equation in all of physics, E equals mc squared. And that equation says nothing more than the fact that energy and mass, which is always connected to matter as a property of matter, are tied together, right? One can be converted into the other. Energy can be made into matter, and matter under certain conditions can be made into energy. The reason why that's important is that it basically says that the fundamental picture, again going all the way back to Democritus and Leucippus, is correct. Namely that if you actually talk about matter rather than all the different kinds of atoms and the quarks and things that make it up, then in fact there is one picture that says there is a fundamental stuff, we just call it matter as a generic name, and it's held together by something that's called energy in various forms, right? 4 different forms of it. But those two are connected by an equation that allows us to explain properties of both. So that sort of seems as though we've gotten to the end, right? We've actually explained what we originally set out. What is the world made of? Well, ultimately it's made of quarks and electrons. What holds it together? Well, the 4 fundamental forces, which are represented as forms of energy, and consequently, we're all done. In which case, I would not have a job, or at least half my job, okay? So that makes me very sad. So of course, what I have to do is to say, well, let me get together with my colleagues and let's actually question the assumption. Are we actually done? Did it all get finished decades ago? And the answer was, for a lot of my career, 25 years or so, this was a very depressing picture, right? It looked as though we'd actually finished pretty much everything that was of consequence. And the really deep questions had been answered. There are lots of ancillary questions with science, of course, but the really deep ones, what is the world made of, what holds it together, had been answered. Now, of course, I happen to live in a time when that has happened. That's a really lucky thing for me, but I didn't do a lot of the work. So obviously, it's better for me if the question isn't answered and there's still exciting questions to pose about what might have happened. So what that does for me is to say, I want to think about what questions we would ask and how we would do those 3 kinds of answers, right? The math, the observations, and the simple language, the common sense language, for saying we haven't finished this trail to the fundamental constituents. And luckily enough for me, it turns out that when we ask those questions, what's the future of physics, it turns out that, in fact, we are not at the end. Not only are we not at the end, we're not even clear that we're at the beginning. But let me explain why. So if we sort of say, what's the future of physics? Most people think, all right, well, we can ask a question, what's next? Well, what's next in this case is, what is the next experiment we would do? What are the next theories that we would write down the math for? And in their minds, what they have is, again, practical considerations, which is the future always involves people being able to travel anywhere they want with self-driving cars, or living under the ocean, or something really exotic. I would settle for just being able to not have climate change, but that's probably not going to happen, at least in the next few years. So the question of what is the future of physics is not tied to what kinds of creations we will be able to come up with technologically. As I said, most of the observations that were made that led to getting to the point of understanding quarks and electrons, and then this whole E equals mc squared stuff, had nothing to do with people figuring out What are we going to do to solve problems that mankind or humankind is actually interested in? It was all about how do we chase down whether or not we're at the end of this 2,500-year quest. And so it turns out that when we ask that question, it's the physics of invisible stuff. Well, invisible stuff, that really doesn't sound like a very satisfactory answer, right? But invisible stuff is actually really important. And so I'm going to ask you a question which everybody in this room will be able to answer. It's a physics question. So I'm going to assert that this whole room is filled with something right now that is invisible. You can't hear it. You can't taste it. You can't touch it, really. And yet, it's vitally important for us. What is it? The air. Okay, so what would happen if I removed all the air in the room? Well, that might happen, yes. It's an old building. Probably the building would stay, but the rest of us would be gone, right? So invisible stuff that you can't see, taste, touch, or even really feel unless you're moving your hands very quickly is vitally important. So invisible stuff does matter. The problem with it is it's invisible, so it's really hard to make observations on it. However, that's never stopped physicists, right? What we do is to simply say we have to define what experiments we can do that would lead to observations. So air happens to be an easy one because I can collect it and I can put it into a container. And I can weigh this. I can also do things that demonstrate to me that I've done that collection and that the collection has been released back into the general environment. So it's actually really possible to talk about invisible stuff in ways that we can measure. So we are not daunted as scientists by saying it's invisible. Our five senses find it really hard to interact with it in a way that allows us to do observations. We just have to do observations that are somewhat indirect. But there's a principle, right? It's not a free-for-all game. The thought has to be that you must be able to weigh it, you must be able to collect it in order to weigh it, and you must be able to do observations in the laboratory that are reproducible when you do these kinds of collections. Now that raises the bar, right? But again, degree of difficulty just makes the game more fun. So we're not so concerned by the fact that it's harder to do those things. That just means that we have to work a little harder, or to actually be honest, we have to make the graduate students work a little harder to get to the point where we can actually make observations that are reproducible, but based on these principles. So if we talk about seeing the invisible, this is really not so hard to do. The laws of physics are compelling, but the laws of physics are not just a phrase, right? These are theories that we can test, and we test them over and over and over and over again. And as opposed to people who think that anything that anybody comes up with as an idea is a theory, to become a theory, and in particular to become a law of physics kind of theory, you have to constantly be willing to overthrow that theory. That is, it takes only a single observation to overthrow the theory of evolution. The fact that we still have it means that no one has ever come up with an observation for which it's absolutely clear that the theory of evolution makes the wrong prediction. And so we keep it because it makes sense of millions of other observations that we wouldn't have a way of connecting together in any kind of intellectual framework without it. The same is true for physics. So at a certain point, I don't need to see direct experimental evidence. If I can do indirect results that indicate that the theory is correct, that's actually good enough to have me believe that, in fact, we've made progress. The progress in and of itself, however, looks a little strange to people who aren't used to dealing with this. So, for example, up here you see a cloud chamber, and the white thing that goes through there is a radioactive source. And so this is nothing more than making the invisible visible, right? There's radiation that's coming off of the source, and what you see in the streaking through the chamber there, whenever there's a little puff of cloud that's a little line, that's a subatomic particle, right? One of the ones that I sort of showed you in the chart earlier, that's being created and is being made visible even though it's normally invisible. What you see up on the screen here is from my demonstration lab back at Penn, which is exactly the same apparatus, but it's time-lapsed, so that what it shows you is that radiation is constantly coming down from the sky, penetrating the room and us, going deep into the Earth, right? So each of those streaks that you see up there is, again, something that's invisible, created outside of our Earth and streaming down from our atmosphere into this room. So invisible stuff is actually all around us. What we needed was to develop experimental apparatus that made it easier for us to see. If you want to go and see what the professionals do, this is something that you can actually pull up on the internet. As I said, you can get involved with this sitting at your home in your slippers. This is, again, a time lapse because it doesn't actually look this dangerous. This would be really bad if there were this much radiation coming down on us. But over several minutes, you can get screenshots from an experiment in the north of Minnesota that actually shows you cosmic rays or cosmic radiation that's streaming down into every area of the Earth. Now, the fact that this invisible stuff exists gives us no real information in saying what the future is going to be per se, right? There might be in some of these observations something new that we didn't expect, but in fact, this is not the answer to the question, or at least a direction that we can see says we're going to discover the next fundamental stuff. It might happen here, but probably not the most likely place that it's going to happen. So we have to turn to something else. And so this is what happened to me. When I went to college, at first I wanted to work with the physics of the sky. I wanted to be an astrophysicist or a cosmologist. And like every beginning freshman, what I did was to find an advisor, or at least I had one assigned to me. This advisor happened to be an experimental astrophysicist. And I came into him and I said, I want to be basically like you. And he said, no, you don't. Really. We don't have the technology right now to make this into a real firm field if you want to be an experimentalist. What you should do is go down the hall to the particle physicists where there's something really, really interesting happening right now and you can get involved with right away. So that's what I did. Now, it turns out that particle physicists are not all that easy to work with, right? So when I went in for my work-study job, because I was fully financial aided, as you just heard from Professor Zilm, financial aid actually goes back a very long way. So if you go to a competitive college, my parents couldn't afford even a single dollar to send my room and board or tuition for college. But Northwestern University provided absolutely everything I needed. But I had to do a work-study job in order to earn enough money to eat. Okay? The first work-study jobs that are offered are, of course, in the library stacking books. The next ones are in the food halls, stacking dishes. None of that sounded very interesting. So out of the entire list of 450 of those, the one that looked most interesting was the one that was in the physics department. There was precisely one position open, and it was in particle physics. So advice from an astrophysicist, go to the particle physicist. An opportunity to work for particle physics. Kismet. That's what I have to do. So I went, and I thought, it's a shoo-in, right? Who wants to work in physics? Nobody will want that job. I was the 13th in line, the last one, and the interview lasted roughly 35, 38 seconds. It consisted of just a few questions. Have you ever programmed a computer? Do you know how to solder? Can you build electronics? Can you design electronic circuit boards? No, 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 no. I'll call you. Literally what he said to me. And so I left with my tail between my legs, really dejected. How could I be a failure as a physicist in my first week in college, already deemed not good enough? However, if you understand anything about where I grew up, is East St. Louis, right? That was part of the Great Migration. Everybody who really didn't have enough money to make it to Chicago from Mississippi stopped in East St. Louis or St. Louis. And so my family stopped, half of them in East St. Louis, the other half in Chicago. And so it's really just Mississippi moved 300 miles north, right? It has southern sensibilities. So I was really dejected. I was really sad. But I also thought, you shouldn't say something that you don't mean, right? So he shouldn't have said, I'll call you, if he never meant to actually call. So it took every bit of courage I had to actually go back and force him to tell me I wasn't good enough to be a work-study student in the particle physics laboratory. I knocked on the door, I stuck in my head, and what do you think he said? He said, I guess you're ready to get started. And I said, no, you said you would call. And he said, there are things that I can teach, and there are things that I can't teach. Everybody who comes in that door, I ask them the same set of questions, and the answer is always no to all of them. You're freshmen, right? Of course you don't know how to do any of that stuff. But all of that stuff I can teach. But what I do is to tell everybody, I'll call them, and I hire the first person who comes back. Now that's a lesson in physics. I didn't understand the lesson at the time, because you can imagine what I'm thinking, right? This dude is crazy. I don't know anything more than I did last week. Why are you hiring me now? And so he put me to work learning how to solder on old circuit boards, teaching me all about electronics and how to use an oscilloscope. And then roughly a week later, Air professor, the senior professor on the project building experiments at Fermilab, came in and said, and I have to give you the whole picture, right? It's a little bit funny, although it takes us a little off topic, right? He's about 6'6", and he had a goatee, and he really looked like the devil. Smoking a big stogie, because even in those days you weren't allowed to smoke in the building, but nobody was going to tell him that, okay? He comes in and he yells out in a booming voice, I hear we got fresh meat. Where is he? That was me. Come with me. So I follow him to the deepest, dankest part of the basement of a physics building, which happened to be the loading dock, and it was a room that was filled floor to ceiling with 20-foot steel beams and bales of gold-plated copper wire. And he said, I'm building an experiment that starts up in 18 months at Fermilab, and I need you to make me 24 planar drift chambers. And of course, my jaw dropped. I had no idea what a planar drift chamber is, let alone how you build one, which of course he knew. And so what was his reaction? He clapped me on the back and said, some assembly required, and he left. At that point, I kind of realized what the first lesson was about, right? Only somebody stupid enough to keep coming back is actually going to make it through this group. But I did keep coming back. Eventually, I did produce all the electronics, all of the boards, and all of the planar drift chambers in 2 years, not 18 months. And I realized that I could be a particle physicist. Now, the whole point of that story is to say that all of that technology that I was supposed to learn how to develop was based on the idea that nobody knows how to do this stuff. We have to figure it out as we go along. And so when I decided to go back into astrophysics after 20 years as a particle physicist, it was around the idea that we had learned something about the technology necessary to make advancements on these two fundamental questions. Have we found all the fundamental stuff in the universe? And that was on the basis of the fact that it had to be invisible, so we needed the right technology in order to make it visible. So what was that technology? Well, it turns out that Einstein had predicted it really back around 1916, which is to say that he gave us in 1915 a theory that he expounded on in 1916 of gravity, which was completely different than the theory of gravity from Newton. And this theory actually does make it possible to indirectly see stuff that is invisible. The way it works is gravity itself bends the path of anything that's moving. And so this is a real picture from NASA of, again, it's a time-lapse photograph of a star passing in front of another star, which happens all the time. But you'll see that the yellow star, the little yellow dot, seems to be moving. Of course, that's not really happening, right? Stars are pretty massive, and the distance between the blue and the yellow is actually really large. So what you're actually seeing is the light from the yellow star being bent by the gravity of the blue. So if we put a grid up there, we can actually see that the light is being distorted. And what that means is that you've got a different picture of how the universe works and how you can find out what's actually in it. Because now, at this point, if we understand that even invisible stuff has gravity, then we can see the effects of its gravity even if we can't see the stuff itself. So now, even if you're invisible, or as astronomers call it, dark, then we can actually know that there's other stuff in the universe, even if we haven't found it in our laboratories, we haven't figured out how to weigh it, we haven't figured out how to gather some of it here and make measurements on it, or have a little bit less here. Okay? And when we did that, or I should say when astronomers did that, what we saw was a really surprising picture, which is that the atoms, the stuff that we spent all these centuries trying to find, and then in the last century actually figured out how to characterize and observe and see that we get down to quarks, all that stuff, all that effort, none of that was wasted. It was just not very useful, because all of that stuff, all the stuff that makes up you and everything in the room, is actually responsible for only 5% of the gravity that's actually out there, which means that most of the stuff in the universe, 95% of the total mass energy, as we call it, is actually invisible stuff, which was a pretty shocking thing to discover 22 years ago, 21 years ago, I guess. But in fact, it's really true. We see evidence of gravity distorting things, like this is a gravity, it should be a nice spiral. It's distorted that way not because of the shape of the galaxy itself, but because the light has been distorted by all the gravity of the invisible stuff that's between us and that observation. So this makes the mission in life for the next phase, the future of physics, of invisible stuff, really, really clear. We might be able to reproduce it in the laboratory by having particle colliders put a lot of energy into a very small volume. And maybe there's some hope that that will happen. But even if it doesn't happen, we will still be able to do experiments on the invisible stuff by looking at what effects it has had on the universe over time. The universe itself is a laboratory, and it's a dynamic laboratory. It changes. It gets small, it gets larger and larger over time, and the rate at which it gets larger and larger over time is actually dependent on all of the stuff, all those fundamental constituents, whether we can see them or not. Their gravity is still there. And by observing the effects of gravity, we can say something about the fundamental constituents and also the energy that's holding them together. So this is called the Large Synoptic Survey Telescope. This is my next project. It's being built right now on a high mountaintop around in a little place called La Serena, Chile. But it's not so important where it is, except that it's really high and very dry. And it's basically a big camera. It's a camera that's very similar in many ways to this one, except that this one has, depending on what version of it you have, between 8 and 12 million pixels. This one has more than 3 billion. It's the largest telescope camera that's ever been devised, and the fact that it exists is not so important because that's technology. But the technology is being put to use for something that has never before been accomplished or even attempted, which is to say, the point of having a synoptic survey telescope is not to have people look through it at a particular target on the sky. That's what the Hubble Space Telescope does, basically. This one is made to simply take pictures of the sky every night, and every 3 nights it sees everything in the half of the southern half of the sky that we can see from South America, and it keeps a record in its pictures of everything that changes night to night to night. So why is that important? Well, first, we've never understood what's called the dynamic universe. When we take a picture, it's like any picture. It's a snapshot. So when you see a photograph or a portrait on the walls in this building, you're getting a snapshot of that person as they existed at the time when the portrait or picture was made. But it would be better, if you wanted to understand the person, if you had a series of pictures that showed them growing up from baby to adult to retiree, right? And the question of how we do this for the universe is answered here. And that's because the further out we look with the telescope, the further back in time we look. So we can see how not only the universe, but everything that's visible in the universe has been developing from roughly 13 billion years ago to just 1 billion or so years ago. but we can also see everything that's happening inside of our own solar system. So this is a record. If you want, it's a movie at very high resolution, very high definition of everything that takes place in the universe that changes over time over the 10-year period for which this camera will be taking continual pictures night after night after night. And from that, we will discover many new things that we never saw before, that we didn't know existed, that are visible. But more important for people like me is that by looking at the form of gravity and how it behaves over time, we will understand those invisible things that I talked about that make up 95% of the mass of the universe. Now, we give them generic names. We call them dark matter and dark energy. But those really are generic names. And so I don't try to describe them because, in fact, we don't know what they are really. And so I can't give you either equations, and I certainly can't give you common sense language understanding of what they are. And at the moment, I can give you some observations, but those observations, we understand, are not yet complete enough to answer the first or the third type of explanation that I mentioned earlier. And so I don't really feel it's important to try and understand how I would say to you, what is dark matter or what is dark energy? Because in fact, it could be anything. At this point, we don't actually know anything other than its existence, how much of it is, there is. And we know a little bit about its properties, right? Dark energy, this room is filled with it. Dark matter, this room is filled with it, right? Every little space that's about like that has one of these dark matter particles streaming through it right now. So through your body, every second, there are billions of particles called neutrinos coming from the sun. There are thousands of these little dark matter particles streaming through you, have been for everybody since the existence of humankind, and we never knew it until just a few years ago. However, the fact that we know that, yeah, it doesn't make you uncomfortable, probably, right? Dark matter is there, but it doesn't seem to have much effect on you. Otherwise, we probably would have discovered that it existed a long time ago. So what we need to do, as I said, is to keep a record of what its effect has been on the universe as a whole in order to actually understand what it does or how its properties actually impact the universe. And so this camera will do that by making a catalog, as I said, of everything that's changed, how the universe has evolved. But there's also other kinds of science that you can do. If you're interested in pure astronomy, like you want to know exoplanets, right, where they exist, this won't be powerful enough to see the planets, but it can actually do follow-up observations of the solar systems in which those planets occur. If you want to know, is there a killer asteroid that's maybe 50 meters across, scheduled to hit the Earth 50 years from now, this telescope will see it. If you want to know, are there supernovas that are exploding stars that are occurring night after night after night? Well, the answer most likely is certainly yes. But if you want to know exactly where they are, what was that star before it exploded? How did it look? We've never, except in very few cases, been able to say, this is what the star looked like before it exploded. So we can say something about what actual characteristics it had before in order to come to the point where it makes an explosion. So for the first time, we'll have all of this record in the database. And as I said, citizen science is one of the things that's a focus for this. So you will actually be able to see all of this information because it will all be freely available and online. So working with companies like Google that makes Google Earth, there will be a Google universe that actually shows you just as much information as you can get from Google Earth, but through the data set of these pictures. But what we want to know specifically is how the universe went from a hot, chaotic state, which we're very clear happened around 13.7 billion years ago, to something that looks much more ordered, much more sensible, and is a lot cooler, right? 13 billion years sounds like a long time, but in point of fact, that time is really precisely described by general relativity in terms of, again, the stuff that makes up the universe. If we didn't have dark matter and dark energy, why would I say that they're important? Well, because if we didn't have them, we wouldn't be here, almost certainly. If you don't have exactly the right amount of gravity coming from dark matter and dark energy, then the universe either evolves too quickly or too slowly. What does too quickly mean? Well, too quickly eventually, if dark energy continues to do what it's doing today, the entire universe will blow up. And what I mean by blow up is not an explosion. It just means that the universe is expanding, and the rate at which it expands is increasing. So at some point, it would be possible that the distance between my eye and my hand is increasing, even though I'm not moving, because space between my eye and my hand is increasing. And at some point, that can be any speed it wants, faster than light. So it actually will be the case someday, if we don't actually understand what the properties of dark energy are, over billions of years, it could be the case that the universe actually just expands into nothingness, basically. It becomes so thin that, in fact, even atoms are separated from each other. There's no existence, at least in terms of what we think. Now, if dark energy had been much larger in the past, that could have occurred before we had solar systems or people in order to study the question. On the other hand, if we didn't have dark matter, then dark matter's gravity makes it possible for things to coalesce together to get this picture of galaxies that you see here in what's called the Hubble ultra-deep field. So that is also disastrous, because it means that things don't develop enough for there to actually be planets to hold together. And again, you don't get life, or at least you don't get us, and you don't get intelligence in order to study the question. It turns out that for the amount of dark matter and dark energy that we have, this 95% being in that form and 5% in the form of everything else that we looked at over the last few centuries, it happens to be just the right amount so that 13.7 billion years is just enough time to get to the kind of universe that we see here. So that sort of looks like either a really lucky coincidence or that there's something fundamental in dark matter and dark energy that had to be the way it is in order to make this possible. Now, the fact that we can do this, as I said, does depend on technology. One of that aspect of that technology is that we can actually deliver the tremendous data that it takes. This will be the biggest data source in all of science during the time that it's operating for 10 years. And that's really huge, right? The only data sets that will be larger than this, once we talk about the simulations that go along with it, are the ones for your credit card companies, okay? It's a true story, right? And so handling all that data means that we need to change the way that we educate students. Computers are much more important. Those students will be doing the same kinds of things they do now in terms of science, but they'll have to do it very differently. They'll have to learn how to apply statistics in very different ways, and they'll have to use what's called data science in order to figure out how to reduce this. But you can help. One of the ways that you help is that you drive some of the questions that are of interest, which is that an important aspect, as I said, is that this database will all be available online. But in order to make use of it, in order to justify the government spending money to figure out how to make people able to use it most effectively and efficiently. For example, you should never have an astronomy class that needs an actual telescope again. That sounds bad, right? Sort of like the biology lab that has nothing living in it. But in fact, this telescope can see everything that's in the southern hemisphere of the sky all the time. So you can have a database any time of the day or night that actually tells you what's in the sky. Anything that you want to study about it is actually available there. And so education should be profoundly impacted by having the existence of so much of that. And so citizen science is one of the things that we concentrate on. Classroom research, how to make most effective use of this, is one of the things that, it's not me, but people like me will be looking at that. Discovery opportunities that citizens can get involved with will be an important part of the study that we will have graduate students and other physicists and astrophysicists actually looking at. Now, the fact is that this doesn't come without problems of some type, right? First of all, this is a very, very expensive kind of instrument in terms of the things that we normally think of as being expensive. But even still, this is around $1 billion, right, to build. And it's around $55 million a year to operate. And so being astronomers, we have to actually raise that money, right? We simply can't ask the government for it. So one of the other things that changes with this is that we have to figure out how to have private philanthropy fund part of the research. Now, I understand that you've probably seen that there are private philanthropy efforts for some kinds of science research that is being done, but nothing that's this concentrated. For this, we will need to figure out how to raise millions of dollars per year in order to make the data that's coming from the billion that's already been spent more useful, and especially for citizens doing science. So hopefully you can expect to see more than that coming up. Now, that means that I have to leave you with an unfortunate endpoint, so I won't bring up the last slide, it's too depressing, which is I've got no ultimate answers, right? Dark matter and dark energy, as I said, those are probably the endpoints, but we don't know for sure because we don't know enough about what they are. So I have to end by saying that's actually a really positive thing, right? So if you're 12 years old right now and just discovering physics, you've actually probably got a good 10 years before we actually know anything very effectively about what dark energy is, or dark matter for that matter. We might get lucky, but most likely it will still be an existing problem. And if there's anything that's beyond that, it will actually be on the back of an experiment like this that we discover the ways in which we will actually make the next advances that go to the next phase of answering those two questions. But it's incredibly lucky that we live in a time where stuff that we didn't know about for centuries, we've actually all of a sudden got the opportunity to study, to actually observe, and to make it all possible to bring it into the home of essentially everybody on Earth that has an internet connection, which I think is a pretty cool thing. So thanks very much for your time. No. Shadows are just exactly what they appear to be, right? That they block light that's coming around, everything that's around the object. So they have an existence, but the existence, again, is an indirect one, right? You know that the light exists, and you know that the thing that creates the shadow exists.
Question here. So in a few minutes, we're going to have our raffle. If you want to hang around for that, if you need to leave, try to do so quietly before we get around to the raffle. Question here?
Yes.
You mentioned that the universe was formed 16 billion years ago.
13.7,
What
yes.
happened before that?
Oh, okay. So the question is, I said that the universe has a finite life. It's 13.7 billion years ago. And the question comes up, what happened before that? So that's another hour-long discussion. But basically, space and time are created along with the universe. So there's nothing before that, because there's no space, there's no time. There's nothing you can say in terms of, what there was, because there wasn't anything.
Are we certain of the timeline? The number?
Not 100%, but I would say like 99%.
Got a question here.
Yes.
How do you know if it's dark matter or dark energy?
How do I know if it's dark matter or dark energy? Very good question. Dark matter, in principle, we don't know that it's different than dark energy. So there are some people who actually do theorize there's a connection between the two. But in principle, we think dark matter is eventually something that we will be able to collect and weigh. Dark energy does not seem to have the property that it's actually collectible, that we can have a little bit more of it here and a little bit less of it there. So it's most likely that we will never be able to do those kind of direct experiments, and that's why we distinguish the two of them.
This guy here? Yep.
How do you suggest that the worlds of the Earth or the universe is expanding? Like, what makes it?
What makes us sure that it's expanding?
Or like, why is it?
Well, there's actually lots of lines of evidence. The most direct one is that if light is coming from a distant object, what we see is that the light itself is in the form of a spectrum, right? Each of the atoms has an independent fingerprint, if you will, of the light that it emits when it's excited. And that light is shifted in terms of its wavelength or frequency in comparison to the light from the same atoms on Earth. And if we ask why would that happen, well, the easiest way to explain why that happens is that the object is moving. And so if you're standing near a roadway and you hear a police siren or an ambulance siren, you notice that the pitch changes, right? It gets higher as it's coming towards you and it goes lower as it goes past you. And so that's called the Doppler effect. It happens for anything that has waves, that travels in waves. Light does that. And so what we think is the frequency shift seems to correspond to objects being further away from us, moving. And the further away they are, the faster they seem to be moving, which would be exactly what you would expect if something is expanding, right? Because if you sort of think about it, things that are close to you expand very slowly. Things that are away from you for the same expansion rate have to be going faster. Constituents, yes.
The first level, how big would that be?
The virus?
Yeah, I don't know.
Okay, so the virus is roughly less than 1/100th of the thickness of your hair. Okay, so really small.
About here are the blue jacks.
What happens when they what? Well, unfortunately, we probably would have seen them before if they actually interacted. They don't appear to actually interact at all. Dark matter, as far as we know, has only really, really, really weak interactions with anything. And dark energy seems to affect things only through its gravity. It doesn't seem to have any ability to change by force interactions with anything else. And so it has gravity, which does the effect, but nothing else.
Right over here. Right.
So just recently there was an article published about people measuring the size of a proton. How do we do that if we can't really see it?
Well, that's a good question. And so if you were throwing darts at a dartboard, right, eventually, if you're really good, you discover the size of the target, the little red dot at the beginning, by virtue of being very good at reproducing the throwing of the darts. And you can see when it hits the center, and you can see when it hits around the outside edge. So that gives you eventually some idea of what the size is. If you're able to consistently throw the dart in such a way that you can see where it misses and where it hits and bounces back. So we actually take that and turn it into math equations, which are quite a bit more sophisticated than what I just said. But it's essentially the same thing. All right, so we can see the size of the protons by actually colliding things with the proton. And the way in which they bounce off tells us something about the characteristic size of what the target is, assuming that we know the beam that we're throwing at it very accurately.
In the red?
Yes?
Dark matter typically holds galaxy clusters and superclusters together
Yes.
to form, bend in space. Is there anything important about those clusters?
Yeah, that's a really good question. So the answer is you have to sort of you have to define what you mean by important, right? And so in terms of the ability for solar systems to form, probably not at that scale. But in terms of having large-scale structure that we sort of see in the behavior of the universe in terms of what we look at, patterns that we see galaxies forming, it's important in terms of the science because it tells us something about, again, general relativity gives us a roadmap, but in order to define the roadmap really well, we need scales, characteristic scales. A map is no good to you unless you know where what the length of a mile is on it. And so these characteristic large-scale structures that we sort of see is one of the ways that we kind of tell what the scale of the universe is and how it's changed over time. So dark matter affects that, and dark energy does as well. So one of the ways we tell the properties of those is we see how that has been changing over time. So it's important scientifically. But in terms of philosophy, do we need that in order to form solar systems or planets? Probably not.
We got two final questions here and over here. So, maybe she's not interested? Nope. Okay, over here.
Yes.
Telescope is constantly taking pictures. No one will ever have enough time to go through them all.
Well, as I said, that's a problem, right? And so we will be well past the point with this telescope of having human eyes see all of the pictures. So we will have to use computers to do that for us. which means that we have to figure out how to teach the computers to actually detect patterns and tell us new things that we didn't expect to see in those pictures. So computers have to become smart. They have to become intelligent.
So,
Well, in fact, in my field, at particle physics, we've actually figured out how to do that, we think, pretty well, which is there's a certain level at which you can train computers to follow aspects of what's called machine learning, which is they can learn the patterns that we feed them very well, and then they can identify anything that looks like a pattern that's not one of the patterns that we've trained it on. So there are techniques that actually work pretty well for doing that we've tested, but they have to get even better for handling the data we're talking about here.
so if there's further questions, we can ask those of Professor Gladney after our raffle, right? Yeah, I'm sure he'll hang around for that. But right now, join me in thanking Professor Gladney again.
Thank you.